there's a board. We're going to use our board to communicate with our computer's keyboard and screen. Okay, so this example, we're going to have our micropad talk to the computer. So the first thing that's going to happen, our micropad is going to send serially the ASCII for a question mark. That question mark will trigger, will tell us, the user, whoever's got the access to the, how do I say this? Whoever's controlling the keyboard, it tells them, okay, time to start typing keys on the keyboard. And what we're going to be waiting for is 10 different keys to be pressed. And each of those keys, as we press them, will appear on the screen. And when the 10 keys are up, we're done. I think I have an exclamation point at the end of the 10. And then there's a new question mark that happens, say, okay, ready to enter new data. So that's the program we're going to write. Let me see one other thing I got to get going here. Okay, so we're going to use 56,000 bits per second, 8 data bits, 1 stop bit, no parity bit, and then there's something called flow control, which we're going to turn off. You can Google that if you want to learn more about it. So to start this, what we've got to do is set up this program called PuTTY, and PuTTY is some kind of serial program that allows the computer's serial to connect to the outside world serial. And so I'm going to show you a lab document. This is not this semester's. This semester's isn't quite ready yet. And this is an appendix in the lab document, which will likely be posted tomorrow, if not later today. Oops, that's not what I wanted to do. Appendix A. This tells you how to use PuTTY. And again, this will be posted sometime very, very soon. First thing to do is to figure out what communication port your micropad wants to use. So when you plug in your micropad, let me actually go back here, move this again. I'm going to unplug my micropad and plug it back in. Come on. Okay, so when I plug it in, we got this little thing comes up, says it was plugged in. And of course, here, this is the thing that tells us, do we want to simulate or use Edge? Nowhere here does it tell us DDBG, it's the debugger. Nowhere does it tell us which port is used. So I'm going to kill that. And so there's something in Windows called the device manager. And if you either hit the Windows key and then type device manager or find it somehow, I'm going to do that right now, device manager, boom. So I'm going to show you that. Device manager. There's something called ports, com/, and LPT. It shows that edge. Again, I'm going to unplug it. Okay, it's not there anymore. Where is device? Don't see it at all. We'll plug it back in. And there we see it. Okay, and it says COM3. That's the key thing, COM3. For you, it might be COM1, COM2, COM7, COM5. I have no idea. If you have a desktop, it's more likely to be a higher COM number because you'll have more USB ports available. So COM3, that's what we have to remember. Okay, and now I'm going to open PuTTY, which I've got to find on my computer. There's PuTTY. And right here, you go to serial. Here, I just found out it's COM3, so I'm going to write COM3. I want to run at 56,000 bits per second, which is baud. I want 8 data bits, 1 stop bit, and turn off flow control. Once you set that all up, go back up to session and say, want to save this. I'm going to call it 4744 spring 21. And you see I have 3744 fall 20. I'm going to save that. And then I'm going to say open. Serial. Sessions. Oh, serial. Oops, let's fix that again. Let's save that. I had to say serial. It was at SSH, that's a secure channel. Now I can say open. And what popped up on my other screen is this window right here. This is the window that we'll communicate with. PuTTY is basically extracting serial input to put on to bring into PuTTY, and serial output, what you type will go out the serial system. And when I say serial, it's the USB. On your micropad, there's USB converter. So on the XMega itself, it's using just the basic serial that we've been talking about. But then there's this chip, this part of the EDBG thing, the debugger thing. That same chip also takes USB and converts it to regular serial. So it does it multi-purposes. Okay, so this is the screen that we're going to actually put some data on. But let me put this to the side for now, and let's start looking at this program. So the device manager is what I use to determine the COM port. I eventually open PuTTY. And now we're ready to run a program, well, start a program. So first, a couple things I want to tell you about. There's this thing called carriage return. And the words carriage return come before computers. It comes from something called a typewriter. You might see those in museums. And a typewriter, when you got typing to the end of a line, you took this little, where is my, you take this and you move it back to the beginning of the line. And that was called a carriage return. Move it to the beginning line. But carriage return also would make the paper scroll up, so you go to the new line. That's called a line feed. And so in some computers, carriage return and line feed are kind of combined, but in general, CR, carriage return, is a decimal 13, and line feed is a decimal 10, and that is ASCII, those are ASCII characters. And so we're going to use carriage return and line feed when we're talking to this serial program called PuTTY, so that we go to the beginning of a line when we get to the end of a line, and then go to the next line, that's line feed. And so I put these so we can just use CR and LF instead of the number 13 and 10. And then prompt, that's my question mark. And you can use whatever you want for your prompt. Like you do a command window, it's usually a greater than, right? If I do CMD, you don't see this, but here, that little greater than, that's the prompt symbol. And the blinking light tells you it's ready. Anyway, okay, I'm going to allow 10 characters. I'm going to read 10 characters in the string until I know the string is over. And so here I defined the string in RAM. My normal jump at the beginning, the stack stuff, I'm going to do that every time. And then I'm going to write a couple programs here. One's called Usart, init Usart pins. So we're going to set data direction and all that kind of stuff. Then I'm going to initialize the Usart itself with the control register settings. And then I've got comments for the rest of it. So let's look first at Usart pins. Okay, so again, we got to figure out which pins are used. And from the lecture, I think it was pins 2 and 3. Yeah, pins 2 and 3. This is in the alternate pin function manual for the transmit and for the receive. And so I just define those as bits 2 and 3. And so let me go down and figure this out. So bits 2 and 3. So let's see, I got my equates. So what I want to do here, LDI for 16, bit 3. Okay, so first the transmit. Bit 3 is the transmit pin. Now, the transmit pin, you got to set it for an output, right? Because you're transmitting. But you want to set it for the value 1. You want to set it to be a high. And why? Because if you set it for low, the system on the other side might think, ooh, start bit, I got a start bit, let's start. But until you're ready to run the serial, it should not be running. It should be idle, and idle is a 1. So the first thing we're going to do is STS port B outset. So that just makes it a 1, and then you make it an output. Right. Good. Okay. Let's see. Next thing, we've got to make the receive pin an input. And so port LDI or 16, bit 2, STS port P dir clear or 16. Okay, so we just set up the Usart pins. So that was called init Usart pins. Okay, the next thing we want to do is initialize the Usart itself. And note, always put nice comments here to describe this so you know what's going on. R16, I'm going to use as my scratch. It's going to get destroyed. I'm going to use all of these registers that'll allow me to set this up. Now, if you look in the manuals, and I'm not going to do the calculation, I assume you can do arithmetic to figure what 56,000 will turn out to be, but it turns out to be P select 5 and B scale -2. And in comments, I have some other values that would work for that speed. Okay, so first thing I want to do is set it for 8 data bits, 1 stop bit, and no parity. Well, let's use our group configurations. So Usart P mode. Let me go over here. I'm going to type Usart P. I just remember one of them, so that'll help me find the other ones. P mode. This is not what I want. There we go. Okay, this is going to have all of them right in this area. So I want to not use parity. Then I'm going to OR that. And a new line, that gives you a new line, little slash thing. And then I want to use asynchronous mode. That's this guy right here. Or how many data bits do I want to use? 8 data bits. And I guess that's it. And then store that. Usart P0, and that's Control C. Control C. Okay. Okay. Let's see. Paradigms Control C. Next, initialize the baud rate. And so there's 2 registers for that. There's baud control A and baud control B. Let me open the Doc 331 manual. No. You can see it. Okay, we're looking for serial Usart. And baud. Okay, how do you spell baud control? Baud control. No underscore. Okay. Okay, baud control A and B. So notice bit select is in the low part of baud control B. And baud control A, it's the high part of bit select. And so high part, low part, high part. So it turns out this guy, we're not going to need this at all because we have a very small bit select. And bit scale is way up here. Okay, so let's go back over here now and write for baud control A, it's bit select, low bits. So that's the whole value. So in general, if this wasn't the whole value, I can say, well, just take the low part of bit select, which I've already defined with equates at the top, and then say usart D0 baud control A. Now, in general, it might be that the top 4 bits of bit select you do need. And so let's do this now, R16. And first, the most significant bits, 4 bits are B scale, right? So the most significant 4 bits are B scale. So I'm going to do this scale. I'm going to shift this 4 bits to the left. So instead of being the low 4 bits, if you just wrote B scale, that's going to be the low 4 bits of a value. Shift it up 4 bits, same thing we're using for the group configuration shifting. So that's moving it to the high 4 bits, and then I can OR it with the high part of bit select, which in this example is 0. Is that clear? I hope. Oh, did I do something wrong with the size? Oh, this should have been the size. Thank you. Okay. Okay. So now I can store that in usart D0 baud control. And I'm spelling baud wrong. My dyslexia is coming up again. Baud control B R16. And the assembler would tell me that. Okay, and so now I'm ready to decide, do I want to turn on the transmitter receiver? Well, in this case, yes. And it turns out bits 4 and 3, respectively, are the transmitter and the receiver. And so what I can do then is LDI R16, and how about this? 1, shift to 4 bits, ORed with 1, shift to 3 bits. Okay, and that's my bits 4 and 3, if I didn't have those defined already, and then save that to a control B, STS, usart D0, control B, 16. And why D0? Well, D0 is what the micropad decided to use. So one thing I didn't look at is the schematics. We'll look at the schematics if we have time at the end of today's class. Okay, let's keep going. So usart D0. So okay, that's the end of the initializations for actually setting up the usart to do the job we want it to do. Okay, so I just got here. So now what I'm trying to do here is I'm going to do some kind of loop. So I'm going to read some characters over and over. But before I do that, hold on. So what did I got? I got my initializations. Okay, I'm going to put the string length somewhere so I can count. So I have all those 10 characters that I told you I wanted to get. So let's use R17 for that. And so R17 has that. Let's have X point to the string. So I have a pointer to be able to store it somewhere in memory. Row string, LDI, XI, string. And I'm going to put the prompt character in R16, and I'm going to tell you why in a minute. So the prompt character is the ASCII for a question mark. So first thing I want to do is I want to output that character. I want that question mark to appear on the screen, to go from your micropad into PuTTY, and PuTTY is going to make it appear on the screen. Okay, and then that tells me I want to read a character. But I'm going to read a character. I'm going to wait because if you put in char, what you're doing is you're waiting for PuTTY to have something to send out. Until PuTTY has something to send out, the micropad's going to be sitting there waiting. So we're going to be in an endless loop waiting for characters to be input. Okay, so we're going to have to define this outchar and inchar subroutine. Actually, let's do that now. Let's go to outchar. Outchar. And I want to, if I need to use a particular register, I want to save it. So I pushed R17 at the beginning because I was using that to count, and I want to pop it at the end. And so now what I want to do in this routine, I want to read the status register to see, hey, before I send something out, I want to make sure something isn't already being sent out. And because I don't want to overwrite what's in the data register. So I'm going to do an LDS R16 or R17. I don't know why I did R17. Status. So what I'm doing is I'm looking if the data register is empty. I'm looking at that. That's what I want to look at. I want to look if that data register is empty. And so this is a good job for one of those skip if bit instructions. So R17 usart deref if. That's that same flag name right there. And EP. So this is bit 5. Bit 5 happens to be the, let's look at the status register, deref. Its spelling just looks funky, but let's see. I think it's the next page. No. There it is right there, bit 5. Okay, so I like when I can to use the group configurations and the bit positions and the bit mask. So there it is, bit 5. And so now I want to say, hey, if that bit is set, that means data register is empty. The data register, if the data register is empty, then I can get out of this polling loop. But if the data register isn't empty, I got to stay in the polling loop. So I'll just put TX poll. And so I stay in this loop right here, asking over and over again, is bit 5 set? If it's set, then I jump over this and I can then, oops, that was the end. I already had that. It's my polling loop. And so I can jump over that and go to, okay, actually store that byte, save that byte that I wanted to transmit that's in R16 and send it out the UART. And to send it out the UART is the easiest thing in the world. Once you set up this system, it's sort of like EBI. Once it's set up, it's really easy to use. R16, boom. Just write the value that you want to send out to the data register. So the only thing you do is you want to make sure the data register doesn't already have something in it. And once you know it doesn't have something into it, put something in. And that's going to send it out. And that's all you need to do. So this routine really, if you know that there's nothing being sent out, is the one-line routine. Store to the data register, boom. Okay, that was outchar, which some people pronounce outchar because they don't remember that stands for character. But the proper pronunciation, if you go out in the world, it's outchar, which I don't get. I call it outchar, outcharacter. Inchar or in character is now the reverse. Now we're going to read a byte that's come in. Well, you can't read a byte that's come in until something's come in. So again, first thing we're going to do is read the status register. R16 usart D0 status. And then we're going to have a polling loop again. And this polling loop is going to say SBRS R16. We're looking for the receive complete flag. And so that's usart RXCIF bit position, which again is bit 7 in this case. And so that's what I got. Skip if that bit. And if that bit isn't set, then I'm just going to jump right back or jump to RX pull. Oh, RX pull. Yeah. So that's not right. I put these in the wrong place. Okay. Now notice that InCare and RX pull, they stand for the same exact thing. So why did I do that? Well, in case I wanted to stick something up here. But I don't have to push or pop anything here because I'm not using anything except R16. Okay. And so now I've done the process. I know that if I got through that loop, then I know there's some data being ready. There's some data that's in the data register. So let's read the data in the data register. LDS R16, same address as for the transmit data return. So that's in-care, out-care, every serial communication. That's the first thing you do. A single byte or single frame, you read that, you write that. That's the first thing to do. You can't do anything else till you've done that. Okay, so let's go back here. So this outputted the question mark. This inputs the first key that you press. And so I'm not going to pass that line until, so I'm going to be sitting, waiting in this in-care subroutine until my first character comes in, which is probably not a good idea. For a big program, you probably want to use an interrupt, and I'll let you do that in your lab, but I'm not going to do that in the lab. So I've got a character. So what I want to do is store that character somewhere in memory so I can remember it. Decrement the counter, which is R17, because I only want to do this 10 times. And so that's the loop. Now the second time through it, so I did my in-care here, and you might have said, hey, I want to see what that character that came in was. It doesn't automatically go to the screen. You want it to go to the screen, you need an out-care immediately after. So I could have done this, input it, then output it. But I don't need to have redundancy here. I've already got an out at the beginning. So when I go back loop, first thing it's going to do is output that character. But because I did it that way, after I get out of the loop, I got one more thing to output. Again, there's other ways to do this. This is the way I decided to do it. And then one more thing I want to output that will just let me know that I'm actually done, R16, exclamation mark. And so I'll just be able to see when I see an exclamation mark that the 10 characters have been received. And then be good to do, let me just copy this. Output a couple times. I'm going to output carriage return and line feed. So it doesn't kind of clutter up the screen. And then I'm going to repeat this forever so that I can run this program over and over. So first, let's see if it compiles or assembles, unless I have some typos. Oh, yeah, there's one. Oh, forgot a parenthesis. Another one. No. Where is my forgotten parenthesis? Do you see a forgotten parenthesis somewhere? forgot a comma after LDR. Oh, thank you. Oh, cool, it's working. Okay, it's not working. I spelled Usart wrong. Usart. I spelled it wrong someplace else. Usart. Usart. And okay. Let's try one more time. This is good. We do real. This is real. This is live. Ooh, okay, it works. So now I'm just going to hit F5. Well, actually, I'm going to put that screen. Well, I guess you can't see both. I want to show you this screen again. Oh, I guess you can. I'm going to hit F5. When I do that, it's going to disappear for a second, but let me just hit F5. It's running. So at the beginning, I'm going to hit F5 again. Come on, come on. Okay. Now let's look at this and see there's a question mark right there. You see a little question mark. And so now it's waiting for me to type. And so I'm going to type the number 1. Whoop, there's the number 1. So what happened is that 1, where is this? The question mark was output, then it was waiting here, and I typed a 1. The 1 was received. I stored it in memory. How do I know I stored it in memory? Let's pause right here. Let's go to internal SRAM. There's that 31. 31 is the hex for a 1. So it stored it in memory. Here we are. So this was stored in memory right here. And then I get to the wrong place, loop, right here. So stored it in memory. Then I go back to loop, and this is where it got output to the screen. So now I'm here again, waiting for the next character. And I'm just going to type now 2 and go back here. 2. Whoops. Oh, I'm paused. Let's hit run again. 2, 3, 4, 5, 6, 7, and I'm going to pause. So we can see those 2, 3, 4, 5, 6, 7. Hit run again. 8, 9, 0. There's the exclamation point and a new question mark. Okay. That's the program. Simple example of serial communication. Okay, I want to run another program now. Very similar program. Now I'm going to actually output a message. Let me see, I forgot what this program was supposed to do. So let me stop this. Let me just do one more so you see there's nothing magic. A, B, C, D, E, F, G, H, I, J. So now let's look, let's pause this. And so apparently 61 is a small lowercase a. There you see it. Okay. Okay. Let's open the other version. Stop this. Got another program called SCI pull red. Okay, so what are we supposed to toggle the red LED only if R or R is entered. So it's going to do a lot of the same things. Set up the pins the same. Oh shoot, I gotta do all that again. Read a character. Okay, read a character is just here. Or call in jar in care. Send that character to the screen. Or call. Okay, so I have an input character now. So what I want to do is compare it to an OR. Okay. I'm going to send a carriage return. CR, I'll call out care. And then I'm going to do a branch not equal to no toggle. So what I'm going to do is toggle the red LED if either the lowercase r or the uppercase r is done. In this case, I'm just going to do the lowercase r. Okay, so if the lowercase r is entered, I'm going to toggle an LED. So branch no toggle. So here I just want to toggle it. And I'll say LDI R16 red. And so somewhere I defined red. No. No, somewhere I'm going to have to define red. Red. Oh, I got a routine that does it at the bottom. Okay. Write the word red. Oh, let's okay. Also, let's write the word red. So I just did a toggle. So I'm going to do a LDI R16 R, and then R call out character. I'm going to copy this a bunch of times and write the word red. RED, and then how about carriage return? Line feed. Get rid of that. And okay, so I toggled the LED. Okay, good to go. And somewhere I've got another program which is called Initialize the Red LED. Initialize red LED, which I've done. We've done this many times before. Bit 4 is the red bit, and so I output that pin to be high to begin, because remember red is an active low LED, so I make it high so the LED is not on. Make it an output pin, and then I toggle it, so now it is on. Okay, and so everything is set. So now let me change the focus, entry file. Let's compile this and make sure it compiles. No toggle. No toggle. There's no toggle. Oh, I forgot the label, no toggle. It's right there. So we're on. Oh, okay, I don't know why I have it twice. Maybe it's not equal, no toggle. There we go. Okay. Let's go back to the putty screen.
Wait, don't you need to also rcall outchar the line feed?
Oh, thank you. Thank you. Let's stop this and okay. Okay, let me F7 again. Almost ready to run. Okay, so there's something here. Clear screen, where's reset terminal? I don't want to really reset it. Thought there was a clear screen reset. I'm a little nervous about this because I don't remember, it's been a while. Let me just make sure that change the session settings are the same. Let's make sure nothing's changed. Okay, good, nothing's changed, fine. Okay, so now refresh, we can run the program. So I'm gonna go back here, hit F5. F5 again, okay. So you guys running? There's no question mark here. I'm gonna type the letter 1, 2 appeared, 3, 4, 5, 6, 7, 8, A, B, but now I'm going to type the R with the road red. I'm going to type X, white. Nothing happens till I hit R, red. Cool. And I could actually make this toggle the red LED if I cared to too. Okay, that's today's demo.